In our body or in any living cell, pH is really important, right? Because pH is control how our body function, enzyme, DNA, cells, how it function. If it's too acidic, everything's died, can't function, so we're dead. If it's too basic, everything's died, we're dead as well. We are dead as well. Okay, so our body need to have some mechanism that control the pH at the right at the right area, at the right pH, right? And by the way, so the pH in our body is 7.4, right? In a biological pH is 7.4. Higher than that, lower than that is really you start dying. Even slightly different, so 7.45, above 7.45, we call alkalosis, which is too basic. And we have acidosis, which is too acidic. Right. Usually, people who have diabetes usually go to acidosis. Just go. Their blood have some ketone. You can go. You can explain all day, but keep things simple. They usually have the condition called acidosis. Anyway, so the mechanism that I'm talking about is the buffer solution. Okay, let's talk about buffer real quick, and then I'll explain it later. All right. So the buffer solution has the ability to resist changes in pH upon addition of small amount of either acid or base. Okay, the buffer solution are made from weak acid and its conjugate base. For example, a solution of acetic acid and the conjugate base acetate. These are a good buffer solution. Bicarbonate and the carbonate. Phosphoric acid, dihydrogen phosphate, ammonium ion, and ammonia. Right? It gotta be weak, not strong. Right? Strong acid, strong base cannot be a buffer. I'll show you why later. All right. All right. So sit back and relax. Let's take a look at the show. In a normal water, so let's say normal water, pH 7. So this is my pH meter. Okay. So pH 7. If I add some small amount of acid, this is what happen. The pH changes drastically, 7 to 4.12. Add a little bit more acid, maybe a few drops, it goes down to 3.07. In a regular water, add an acid, pH change dramatically. Now, go back to a normal water, pH 7, adding a little bit small amount of OH, the pH goes up drastically to 8.56. Add more OH, add more base, pH change drastically to 12.45. Okay, so water, pure water, or any solution that doesn't have buffer, pH change dramatically if you add a little acid or add a little base. All right. Now, in a buffer solution, so we have an acid and a conjugate base. So an acid, so let's say this is acetic acid, which is an acid form, got a proton, and a base, which has got a negative sign right there. So this solution is filled with some amount of acetic acid and acetate, conjugate base pair. Okay. Now, if pH is 7. Okay. If I add a small amount of acid in this solution, what's going to happen? Well, the pH of the solution doesn't change right away, because when you add an acid, well, this solution already have a base, so a base waiting for it. So the base, when you see acid, go grab acid right away. Acid-base reaction. So acetate will receive proton, become acetic acid, and acetic acid is already in solution, right? Acetic acid does not decrease the pH, so the pH doesn't change that much. Yeah, that's what the buffer solution for. Now, let's say in a buffer solution, same buffer solution, so it's pH 7. Okay, let's say we add a drop of hydroxide, so a little drop of hydroxide ion. In a regular water solution, pH goes up right away, quickly, drastically, right? But in a buffer solution, well, we add a base. In the buffer solution, already have an acid waiting for it. We have an acid here, acid here, acid here. When this acid molecule see the base, go grab the base right away. And acetic acid react with hydroxide ion, become acetate and water. And these two, acetate and water, does not change the pH. I mean, change just by a little, but not a lot, right? And pH doesn't change that much. 7, 6.99, same thing. Right? So my point is a buffer solution resists pH change by doing reaction with it. Or the conjugate acid and base in the solution react with an acid or a base that we add into it. Right? If we add an acid, the conjugate base will go into action. If we add a base, the acid will go to do action. Okay, and the buffering capacity, which is the effectiveness of the buffer, is at the hold on. Okay, the effectiveness of the buffer solution depends on the amount of acid and conjugate base. 0.1. If we have a buffer solution of 0.1 molar acetic acid and 0.1 molar acetate, that's the amount of acid and base that it can withstand, right? If we add an acid or base over 0.1 molar of any of this, well, buffer solution is not buffer anymore because these two get used up, right? If we have 2 molar of the acid and 2 molar of its conjugate base, that's the capacity. You can add an acid or a base up to 2 molar before these two get used up, right? So this guy have the highest capacity to resist pH change. Okay. All right. Concept test real quick. So, which of the following combination would be the most effective buffer solution? All right. Number 1, citric acid. So citric acid is an acid in like a lime, lemon, right? So like citrus juice, citrus fruit. Okay. Anyway, so citric acid is a type of is a weak acid. So we have 0.01 molar citric acid and 0.01 citrate ion, compared to 1 molar citric acid and 1 molar citrate ion. Totally, the 1 molar beat 0.01 because the capacity is 100 times higher, right? 1 molar citric acid and 0.01 molar. All this is too low of the conjugate base. 0.01 molar citric acid, too low of the acid, right? The highest capacity, so this guy can withstand addition of acid or base up to 1 molar, not just 0.01. Okay, all right, that's how buffer solution works. Now we're going to move on to the non-buffer solution. Okay.